Physics 2018, this is Mr. Lewis. Hopefully this will be the last video going over the study guide. This is the fourth one. I'm going through the simple machines. I'm going to try to blast through these last five as quick as I can because I don't want to try to do a fifth video. You all have already probably watched enough if you've watched the whole thing. So I already did number 19, that was the wedge. So moving on past that, we have Schmo's playing in a junkyard. He's accidentally knocked a pile of cars onto himself. Well, Schmo's an idiot, so, you know, he needs some help. Joe's going to try to lift this car off of him, but he's not strong enough. He needs to lift a 3,500 Newton car, but he can only lift 700 Newtons. Problem. Easily solved with a machine, because the whole point of machines is to take your input force and amplify it to a larger force. So all we need is a machine that can take 700 Newtons and multiply it up to 3,500 Newtons. So the output force is going to be the car. The output is the thing that we are trying to lift. And Joe, obviously, he himself is the input. So actual mechanical advantage, this first thing that it asks for, if he can find a machine to help him, what actual mechanical advantage does it need to have? What is the multiplying factor that we need to be able to get? Now, some of you can probably see what this is in your head, but just for the sake of using the formula, remember that AMA equals force out divided by force in. So the output force goes on top, the input force goes on the bottom, and as I just told you, remember the input is going to be Joe, and the output is going to be the lifting of the car. So AMA is going to be the output of 3,500 divided by the input of 700, which equals 5. 3,500 divided by 700 equals 5. So that's what the actual mechanical advantage needs to be. No algebra involved, just divide it straight up. Now, suppose he finds himself a lever. So we're going to take a steel rod, wedge it under the car, put us a pivot point, a fulcrum underneath it, and lift it with this lever. So he can jam it under the car and get leverage over a fulcrum that's 0.5 meters away from the car. So the distance here, why is that important? Well, let's look up at the equations for levers. So the lever equation, lever IMA, is length from pivot to effort divided by length from pivot to resistance, or L effort divided by L resistance. So, whoops, I've rearranged things I didn't want to rearrange. Yeah, so if I zoom in again on my picture there, what we're looking at is, oh, that's too far. So LR here, so let's assume that the car is on this side of the lever. So on this, look where the mouse cursor is. So on the left side of this here lever, on the short side, we've shoved this tiny end of the steel rod underneath the car, and we're going to lift it over this fulcrum. And Joe is going to push down on this side, the long side. So what they've given us in the problem is the length, or the distance rather, from the fulcrum to the car. So that's going to be the load length, the distance to the load, or the resistance, whichever way you want to point out that word. So let's shrink that back down. So in our length effort divided by length resistance, what we have is the resistance. We have the denominator, we have the bottom number. And we also have the IMA, because the next point of that problem, it said, assume that it's a perfect 100% efficient lever. So if it's 100% efficient, then the actual mechanical advantage would be the ideal mechanical advantage, because that's what ideal means. Ideal means perfect. And if this is a perfect lever, then you would actually get all of your mechanical advantage. So I can just say then that IMA equals LE divided by LR, just like the equation said before, up there at the top. And then I'll go ahead and say the IMA that we wanted for this machine was to be, we wanted it to be 5. So 5 equals the length of the effort arm divided by, it tells us that it's 0.5 away from the car. So that is the resistance, that is the 0.5. So 5 equals L divided by 0.5. Remember, if you like that better, you can just change this out to be X. So 5 equals X divided by 0.5. How do you solve that? Changing it back to lever. All you would do is multiply the 0.5 over to the other side. So ultimately, our length of the effort arm is going to be 2.5 meters. There we go. Problem solved. 2.5 meters from the fulcrum is how far he needs to be out. So again, if I look back up at that picture, the long side of the lever, the side that Joe is going to be using for his purpose, it's going to need to be 2.5 meters long, and then Joe will push all the way at the end. So as long as he gets himself a lever that's big enough, he will be in good shape, and he can save Schmo from his car squishy death. So 21. Now we're looking at a screw. Screws usually have insanely high mechanical advantage. That's how screws function, mostly because they're very inefficient, so they need that high mechanical advantage before they can actually do anything useful. But they move very slowly. That's the trade-off for the mechanical advantage. Like we talked about in class, once again, mechanical advantage, the whole way that it works is, yes, a machine will give you more force than you were able to put in. It will amplify your force. But the trade-off for that is you have to give up distance. If you have a screw, you have to turn it a whole bunch of times to make it go a very short distance down into whatever you are screwing it into. However, that's not the only kind of screw that exists, unlike what some of your presentations seem to have suggested. Not trying to throw any shade, I'm just saying you missed a different kind of screw. So there's also the kind of screw, it's called an Archimedes screw. Let me Google one here real quick for you. Archimedes screw. So it looks like this. So it's a screw inside of like a long, tightly sealed shaft, and what it's done is you put it on an angle and you use it to lift water out from a small reservoir up to the top of a hill. Basically, when you turn the screw, you can imagine in your head that the screw is turning. If you or think about a barber pole. When it's turned, it's going to look like that the actual individual ridges are moving upward, as long as you turn the crank the right direction. So the water will literally just travel up that screw. You're going to turn the crank, which will be the radius that you would be using as the screw head or the screwdriver, whichever way you want to look at it, or your ratchet, however you looked at it before. That's going to be the radius of that. And then the threads are clearly much further apart than on an actual screw. And these are a much more reasonable mechanical advantage, and actually possibly not even a real mechanical advantage at all. But it should be, as long as your crank is big enough. So let me go back to the problem. We're going to have another type of screw, an Archimedes screw, blah, 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 blah. Suppose the Archimedean screw has a 1 meter crank. So remember, the crank is the thing that you're turning, so that's the radius in the equation. And its threads are 0.5 apart. That's the pitch. Remember, pitch is the word that tells you the distance between two threads on a screw. So in between two of these slanty bits, the distance between those, that is the pitch. That is the thread distance, however you want to phrase it. So let's go get that equation for screws out of our original formula sheet. So screw is right here. So we're going to do 2 pi radius times, or divided by pitch. So copy, let's paste this down here. And IMA equals, paste, 2 pi r divided by pitch. So let's plug in the information that we know. The IMA is what we're solving for. That's what would be the IMA of the screw. There we are. So IMA equals 2 pi has to stay the same. Paste. Crap. I want that pi. Copy. 2 pi. The radius is for the crank. So the crank has a length of 1. So that is the radius. And then we're going to divide by the pitch of the screw, which is going to be the 0.5. 0.5. And again, no algebra involved. I can just plug this straight into the calculator. So 2 pi is 6.28. Multiplied by 1 is 6.28. And then divided by a half is the same thing as multiplying by 2. So the IMA of this screw is, oops, I don't want that B there. It's going to be 2 pi effectively times 2, which is 4 pi. So 4 pi is going to be, let's just simplify it to 3.14 times 4. And my calculator says that 3.14 times 4 equals 12.56. I should have been able to do it in my head, but I am not on the ball this evening. So 12.56, IMA, there you go. Next up, if you turn the crank with a force of 300 newtons, how much weight could the screw lift? So again, this is using the actual force ratios here. So remember, what is the whole point of a machine? It amplifies your force by the number that it is. This is a multiplier for force. That's what mechanical advantage tells you. So if you turn the crank, you are the input. The machine is amplifying your force. So you really don't even, if you understand the concept, need the equation for this. You can just know that this 300 newtons is going to get multiplied. And it's going to get multiplied by the mechanical advantage of the machine. That's the whole idea of a machine. So 12.56 times 300 equals your force output. So what is that number? It's going to be, no, come back, phone. I need you to do things for me. Times 300, 0.68 newtons equals the force output. That is how much weight, how much force that this thing can lift. So it's actually a pretty solid screw. 12.56, not totally unheard of, especially for an Archimedes screw. I mean, it needs to be at least that much more to lift insane amounts of water. I mean, water is heavy, y'all. It's not a light thing to lift. And imagine now that this entire thing is filled with all of that water. I don't know that this is actual size. Well, obviously it's not actual size, it's a picture. But this crank, if that's enough water, would probably take multiple people to turn it, because that's, even with the higher mechanical advantage, that's a lot of water to try to lift. I mean, think about how much a gallon of water weighs. This has got to be just tons of water in this screw that it's got to lift all at the same time. So it needs that high mechanical advantage of 12 at the very least in order to even really be that useful for the purpose that it is assigned. All right, I got 4 minutes left. Pulley. I'm not going to get through all of these. So one was the IMA of these pulleys. This is really simple. Remember, all you do with pulleys is you take the load part, which in this case, on the green one, is going to be this entire bottom assembly. The first pulley, the second pulley, and the mass itself. All three of these pieces are attached by this green line. This, imagine it's a piece of wire or a brace. The top pulley is attached to the ceiling. It's not directly attached to the load. So if I circle around the load, how many strings do I cross? How many are attached directly to the load? Well, this one is attached to the bottom pulley. This one is attached to the first pulley. That one is attached to the first pulley. And this one is attached to the bottom pulley. So 1, 2, 3, 4 strings. So the first IMA is going to be 4. So green equals 4. And then blue, again, let's check what our load piece is. So the load is going to be these bottom 2 pulleys attached by this bar, and then this mass, which these blue lines here at the very bottom, these are not parts of the rope. So the rope is running through the pulley right there. So these are not part of the mechanical advantage. This is just like the assembly that's holding together the pulleys with the mass. So how many ropes are attached to the load directly? I cross 1, 2, 3, 4, 5, circling around the load. This one is not attached. This one goes only to the top pulley, which is not attached to the load. So this one doesn't count. Only these 5 here at the bottom are going to be important. So IMA is going to be 5. So green one's 4, blue one's 5. Pulleys are really easy. No math, just counting. So the picture on the test will be very similar to these. It'll be one of my crappy hand-drawn ones. So just pay attention to where the load is and count your strings. Number 23, we have this loading ramp. It's going to be 5 meters long and 2 meters high. So remember, ramp is the same thing as an inclined plane. So the inclined plane was the very simplest one. The diagonal length is what we're looking at in this case. Remember, that's not the same as the wedge. The wedge we wanted straight across. The inclined plane, we actually want the diagonal. And I pointed that out here in the plane IMA. Diagonal length divided by height. So it's L divided by H. And if I go back down to the problem here, we have, it says that if an actual mechanical advantage of 1.25, how efficient is the inclined plane? Oh ho! So I'm actually giving you a little bit of a curveball here. I'm asking about efficiency and giving you actual mechanical advantage. So I didn't give you the IMA yet, but like I just showed you, you can get the IMA from this, from length divided by height. So let's go ahead and do that, because it's probably going to be needed to actually get the efficiency. So 5 divided by 2, length divided by height. This is IMA equals 5 divided 2, which of course equals 2.5. Now efficiency, as I told you at the beginning of this, is going to be AMA compared to IMA. So that's the other equation for efficiency. So efficiency equals AMA divide IMA. So that's AMA given in the problem. So if I go down here, the efficiency is going to be 1.25 divided by that 2.5 that we just got for the ideal mechanical advantage, which means that our efficiency is 50%. That is not a 50. There we are. Jesus. Okay, I'm out of time. Apparently I can't type today. 50%. All right. B, how much work is actually done? Again, use the efficiency equation. Sorry, I'm done. I'll get you later.